This video is about a low noise oscillator that you can read about here on the internet. It's this unit. It is an amplifier with two outputs, and the cable you can see goes from one of the outputs to the input. Inside here is a narrow crystal filter, and you can read on this internet page about all the details. There is schematic diagram and other stuff. And what I will show here is how this behaves when it is run as an amplifier and with feedback, with gradually increasing feedback, because that makes it a Q multiplier and eventually an oscillator. I have connected attenuators and a directional coupler. From the feedback output here, there is a first attenuator and then a second attenuator here. And this one is now set to Z0, it means infinite attenuation. And then through a directional coupler, and into the directional coupler I connect the test signal from a network analyzer. And this is what I can see. The sweep width, the span, is 2 kHz. And you can see the phase switches at the point where the signal is maximum. And the attenuation is 20 decibels because of the directional coupler. So the network analyzer, which indicates 0, actually means that the gain is about 20 decibels. Now I insert a little bit of feedback. I press 10 decibels. And you can see the signal becomes a little bit stronger. There is positive feedback. 10 decibels on one of the attenuators, but there is also 5 decibels on the other one. So I increase the signal. Meaning I increase the feedback. So this is the classic Q multiplier. And I have to rearrange things a little bit. So I removed one of the attenuators, and there is now 5 decibels in the remaining attenuator. And this is what the network analyzer shows. The gain has increased from 0 to 13. Remember, there is another 20 dB in the directional coupler. The sweep speed starts to be a bit high for this very narrow peak. Maybe best is to just change the sweep width. Frequency, span, 0.5 kilohertz. And the center should be maybe here. Well, that was obviously very difficult for this machine. The span is now 500 Hertz, and the frequency 14.1585 and with 5 dB attenuation. So I changed that to 4 dB and Q multiplication becomes bigger. Three dB. And now you can see there is some artifact on the peak. So I change the, let's see, change the power level first. Level, it's minus 20, I make it minus 40 instead. And the signal went a little bit stronger. I have to sweep slower to see what's going on. So that is frequency and span and 100 Hertz. And now I can reduce attenuation 1 more dB, and now it's an oscillator. So I add fractions of a dB, 0.2, 0.4, it's still oscillating, 0.6. And I don't know what this ringing actually means. Probably the signal is a little bit too strong. Power, minus 60 dBm. No. Average system bandwidth, run it slower. The bandwidth is so narrow, so I have to run very slowly to get the correct display of the frequency response. And the gain is now, when I sweep slowly enough, you can see it is 38 decibels extra gain because of the positive feedback. The unit is now running as an amplifier. There is no input, this is just the noise on the output. I have disconnected the feedback here, and the input is connected to this signal generator here, and right now it's switched off. First I want to look at the noise floor. This filter that is applied in Linrod, I can probe for the 3 dB points about here, 437 Hertz to 486 about. So this is about a bandwidth of 50 Hertz. I can read the noise floor here in the S-meter graph, like this. And I feed the value I get here. sorry, I had already 18. I make this 0 and read the value again and feed minus 78 into this box. This way the noise level on the peak will become 0 within 0.3 dB this time. So I move 1 kilohertz away. This will be about here. 1. And then wait for the noise level. And you can see it's about 16 decibels. So here, still 1 kilohertz away, the S-meter shows me that the noise is 15.8 dB. Well, I don't measure the decimals carefully, so 16 decibels lower is the noise 1 kilohertz away from the center of the passband. And I go 1 more kilohertz away, it will be about here. And then, as you can see, the noise floor steps down another about 2 dB. So, at 2 kilohertz I see 17.5 decibels below the noise at the center frequency. I now inject a signal of minus 100 dBm. Like that. It means minus 120 dBm because of the directional coupler. It comes from here and through this directional coupler. So it's minus 120 dBm, and the level now comes out as, what can it be? 17 decibels above the noise floor in 50 Hertz, about. That means that the noise floor is 17 decibels stronger in 1 Hertz, that's 34, which means that the noise floor is at minus 154 dBm at the input. And that means that the noise figure is about 20 decibels. Now I connect the feedback. The attenuator is on 5 decibels. And you can see the noise increases near the center here, but it doesn't increase, let's say 200 Hertz away, which would be here. Place the mouse there again and remove the positive feedback. And you can see the feedback seems to attenuate the noise rather than amplify it at a separation of 200 Hertz. So I add again and then set the attenuator to 4 decibels. And the noise peak becomes sharper, but the noise at 200 Hertz does not increase. So 1 more decibel of feedback. And now the noise peak is rather narrow. But it seems that the noise outside about 100 Hertz does not increase due to the feedback. It's a Q multiplier we see here. So 1 more dB of feedback. And now it's an oscillator. So this is the point where it oscillates. And here is where it doesn't oscillate. You can see here the amplitude margin tells what is the total signal level. So here is the noise spectrum with feedback just before onset of oscillations. And now you can see the same but without any feedback. And it seems that the frequency where feedback increases noise is about plus minus 100 Hertz. So here is the spectrum. I have expanded it considerably, so you can see 100 Hertz is from here to here, and this is with feedback. And I place the mouse here to remember where the noise level is, and then I disconnect feedback, and I have to wait for a while. And it's very clear from the waterfall here that noise increases in about 100 Hertz wide range around the center, where outside that region noise is independent of the feedback level. I now inject a signal generator at minus 100 dBm. And it comes 48 decibels below saturation for this receiver I'm using. I had to change the generator because I need 1 Hertz step, and even that is not perhaps quite fine enough. So this is minus 100 dBm. I increase the level. Increment set in the steps of 10 dBm. 10. And you can see on the waterfall the carrier becomes stronger but the noise doesn't change. 20. 30. 40. 50. And now it's close to saturation, so I cannot go further. Well, 6 dB from. And you can see here we have noise. That is the reciprocal mixing because of this receiver. I don't think that this amplifier, it operates fully linearly. It shouldn't add any noise just because the signal becomes a little bit stronger. I don't think so. Now I have applied a potentiometer to get a continuous gain adjustment. And I have set it just below onset of oscillations. And this is what I can see on the linear screen. I have expanded the frequency scale, so we have 10 Hertz from here to here. And the noise peak is here, and you can see how the noise density changes with frequency. The level is 60 decibels below saturation for the SDR-IP, and I have 12 decibels of gain, low noise gain, in front of it. So with just a fraction of a tenth of a dB more feedback, oscillation will start, and then the radio will saturate. What conclusions to draw from this is beyond my skills to know, but I think the measurements I've presented here gives a fairly good characterization of the performance, and somebody who knows how to do simulations could compute what is going on. Now feedback is higher, and you can see that there is a thermal stability problem. I would have to put the unit into a thermostat to get it frequency stable. To see the slope on the noise floor, I can increase averaging. It's now 2, and I make it 10. Which means it will average over about as much as the height of the fonts here. Now I can compare the noise 2 Hertz away. It's about from here to here. We have 35. And 4 Hertz away, that's here. And we have, what can it be? 27. And on the other side, 2 Hertz away is about here, 37, and 4 Hertz away is here, 30. And of course the thermal drift widens the peak here, so we cannot measure very close, but it looks like the slope is 6 decibels per frequency doubling. I now remove the feedback, disconnect like that, to see what happens to the noise. And it takes some time before we see anything here because of the averaging. But here it's obvious that the wide range noise has not changed. Only the noise very close to the center is affected. And now we can see that there is a dramatic effect very close. So I compensate that by adding 10 decibels more, minus 10. And that's not enough. Minus 30 then. And here you can see where the noise is. And adding 30 decibels here means minus 10 at this point. Like that. So now I added 30 decibels. So you can see at something like 5 Hertz from the center frequency, the noise was reduced by 30 dB when I removed the feedback. And I put feedback back like this and change the resolution to run things faster. Like this. And I run the S meter faster. And the measurement bandwidth is about 50 Hertz as before. I haven't changed that. Now I will turn up the feedback just a little bit by reducing the attenuation. And I look at the S meter here. And now I'm not turning anything anymore. The amplitude just rises and rises linearly. It means, and here we reached a point where something happens. The limiter goes into limitation. And if I try to look, what does it look like? Minus, 0, 30. So now it's an oscillator, it's no longer a noise amplifier, 60. And here you can see the carrier. So once I reach a certain point, there is an exponential increase, which manifests it as a straight line on the S meter logarithmic plot, and the level increases until there is some nonlinearity. And again, I disconnect feedback. There was a key and click. And you can see that 10 Hertz away, the noise floor was 27 dB above the noise floor. Well, the noise floor dropped by 27 dB. I think this is mainly because of the SDR IP, but there is no way for me to know.